Here's the integral of u to the n. Remember that u is some function of x. It can be equal to x, and if it's simpler for you to remember this the first time you go through this, then maybe you should. But u to the n, du, the integral of u to the n du, where n is any real number except minus 1, is u to the n plus 1 divided by n plus 1. And again, it can't be a minus 1 because here you would have division by 0 plus the constant of integration. Special case, when the n is a minus 1, then that's the integral of du over u, which is a natural log of the absolute value of u plus c, because the logarithms of negative numbers don't exist. The integral of the cosine of u du is the sine of u plus c. The integral of the sine of u du is minus the cosine of u, because the derivative of the cosine is minus the sine, times this minus gives you the original sine back. Remember, the derivative of each one of these guys is going to be what you started off with under the integral sign. So you already know these from the derivative formulas. The integral of secant squared of u du is the tangent of u, and the integral of e to the u du is e to the u. And always you have a constant of integration. So that's kind of the chain rule, or we're going to go into the substitution rule, or Dr. Seuss used to teach here. He called it a chain rule for integrals, and that's a good way to think of it this way. You're using, instead of x, you're using functions of x, which are named u. Some people in this book calls it the substitution rule. I have heard students call it u substitution, because almost always that's what you do. You substitute u for some function. In many books, and I'm telling you all this because you may use different textbook as you're studying some of this material. In many books it's called change of variables, which is a pretty good description. But so let's go through the theory of this as it's presented in the book, and then I'll show you some shortcuts that you maybe can take advantage of. Let's try. I'm going to use an example that I think I gave this problem earlier this week. Suppose you had the integral of the cosine of x, cosine of 2x dx. What's the integral of the cosine of 2x dx? Well, here's the u, just like in the chain rule. Remember the chain rule, it was almost always easy to recognize what the u was. It was embedded in some trig function or under some inconvenient radical where it was not a perfect square or something like that. Here's our u. Okay, here's our u. So you do the and here's the order. U is equal to 2x, right? Let me describe what we're going to do. We're going to convert this from a complicated problem to a less complicated problem by doing this substitution. Because right now we can't integrate this. Well, I guess we could use double angle formulas, but let's do the problem the way it sits. U is equal to 2x. Now I'm going to show this one time, and from now on you can skip this step and go to the third step. Then du over dx is equal to the derivative of 2x is going to be 2. But what you want to do is you want to write it this way. Du is equal to 2 dx. So from now on I'm going to go directly from here to here. And in fact, I'll do it now so that you can get used to it. So if u is equal to 2x, then du is going to be equal to 2 dx. Now, if you look at this, we don't have 2 dx. We only have 1 dx. I'm going to leave a space there and just to show you that. You have a 1 dx. You don't write the 1, but just imagine that it's there. Now, how do I get 1 dx out of this? You divide both sides by. So here's 1/2 du is equal to dx. The process is to get rid of all the x's and replace them with equivalent u values. You cannot have x's and u's and t's under the same integral sign. You don't do that until you get maybe to Cal 3. But in Cal 1 and in Cal 2, all of your variables of integration have to be the same. So you have to get rid of all x's. You can't have any x's, and you can't have a mixture of x's and u's and t's. Just one variable. And in this case, We're converting everything over to u. Now here's, you got to replace everything. You got to use all the material you're given and no more. You got to use exactly what you're given and convert it. So this becomes the integral of the cosine, and instead of 2x, I'm going to replace it with cosine of u times, and then instead of dx, remember dx is going to be 1/2 du. Now, what did I tell you earlier about constants? They float across the integral sign with no penalty. So this becomes 1/2 the integral of cosine of u du. So this is going to be 1/2 the sine of u plus c. Now, if you want to, and normally you're required to do this, especially in a test, you go back to x's. So this becomes 1/2 the 1/2 sine of 2x plus c. Again, you don't have to check this unless you want to. Take the derivative of this. If you take the derivative of this, well, this is a constant, so you can put, you can say prime, okay? So here's a 1/2, that's constant. The derivative of the sine of 2x is going to be the cosine of 2x by the chain rule times the derivative of 2x, which is equal to 2. The derivative of the constant c is 0. 2 times 1/2 is 1, so you wind up exactly where you want it to be. You wind up exactly with your original problem. This is a way to do it in a formal substitution method. Let's try another technique. Now, so this substitution rule, this is not in your text. I made this up, so this is kind of informal. But there are 3 possibilities. First of all, the general function cannot be integrated. In our library, we have a book with several hundred pages with thousands of integration formulas. But still, there are some functions that cannot be integrated. But your professors are not going to give you something that can't be done. Okay, so you can assume that anything your teacher gives you to integrate, you'll be able to do. So here's case 1. Here's what I call case 1. No changes to f of x. No changes to what you got under the integral sign. You don't have to do anything, and you just use the chain rule form of the integral, and you can find out what your problem is. For example, what is the integral of the square root of x plus 1 dx? Okay, instead of the square root, I'm gonna put a 1/2. Well, if this is obviously the u, right? This is the u, and the derivative of x plus 1 is going to be just 1. So what you can do is you can just go ahead and say this is going to be x plus 1 to the 1/2 plus 1, 1/2 plus 1 equals 1/2 plus 2/2, which is equal to 3/2, right? To the 3/2 divided by 3/2, which you will rewrite as 2/3 x plus 1 to the 3/2, and plus the constant integration. Okay. So you had to make you did not have to modify this at all. You didn't have to multiply it by anything or anything like that. Okay. So and you can check this, calculate the derivative. You bring in 3/2 times 2/3. That's going to be 1 x plus 1 to the 1/2 because you knock down the power by 1, and then times the derivative of x plus 1, which is 1, which is exactly what you started with. So that's what I call case 1. Here's case 2, and that's insert. You can insert constants. And you should do this when you can, okay, if it's possible. Let's go back to our previous problem, our old friend, the integral of the cosine of 2x. This is, and you can do this by inspection, and you'll get the proper answer without going through the formal substitution. We're going to calculate the same problem using this insert constants, or, and you'll understand what I'm talking about. Here's the integral of the cosine of 2x. I'm leaving a space here, dx, okay? This is obviously the u. This is the u. The derivative of 2x is 2. So I'm going to put, now this is du, right? But if I put a 2 in here, what do I have to put in front to counterbalance it? What do I put in front so that you have not changed the value of this? I put it 1/2. So this is equal to 1/2 the sine of 2x plus the constant integration. The third case means that you have to make, case 3 is have to use a formal method. And an example of this, here's an example of case, what I call case 3. You have the integral of x over the square root of x minus 1. Okay, dx. Now, obviously here's our u, in case you missed it, okay? Again, the u is always under a formidable radical, or, this is not a perfect square, so you can't take the square root of that. So here's our u right there, okay? So we can't just add a number here and then do tricks like that. We have to actually do a formal u substitution. So the u is going to be equal to x minus 1, and this implies that x is equal to u plus 1, right? X, you just put the 1 on the other side and get. Then du equals dx. Okay? So our problem now becomes the integral of x, and x is equal to u plus 1, divided by, this is going to be x minus 1 to the 1/2, but x minus 1 is equal to u, so it's going to be u to the 1/2. And then times, instead of dx, I'm going to put du. So everything is now in terms of u. Okay? So now what I do is I divide each of these guys in the numerator by u to the 1/2. And we get the integral of u to the 2/2 minus 1/2, so it's going to be u to 1/2 plus, and then this is going to be 1 divided by u to the 1/2 is going to be u to the minus 1. And take the integral of that. So this is going to be equal to u to the 3/2 divided by 3/2. Remember, you can check this power rule for integrals because these two numbers have to be the same, right? Plus, and u to the minus 1/2 plus 1, that's going to be u to the 1/2 divided by 1/2. And we'll add the plus c at the very end. So that's going to be equal to, this will be 2/3 u to the 3/2 plus 2 u to the 1/2, and finally we go back to the what is u equal to? U is equal to x to the minus 1. U is equal to x minus 1, so you go back to that. So here's 2/3, and then x minus 1 to the 3/2 plus 2. We can put the square root of x, I guess. But I'll go ahead, and since I'm using fractional exponents, I'm going to call that 2.5 plus constant integration. Okay? So there you had no choice but to use the formal substitution rule, or change of variables, or chain rule for integrals. You should work several problems like this and try to use the, as often as you can, see if you can stick in a number and make it work. That is, try to see if it's case 2. That's the kind of the ideal case. Actually, the simplest case is what I call case 1, where you have to make no changes at all.